So hello everyone, this is lecture 80 for the mathematical physics. In the last lecture we have started Green's function, and let me revise you for that what we did in the last lecture. So it is a method used to solve a differential equation where we have some inhomogeneous term that is called source term fx. So if you just change this function fx, you can just solve this directly using the Green's function. And see, this L is nothing but this operator, means take this y out, then whatever differential operator is remaining is called the L. Then the solution of this equation can be written in this form: yx equal to a to b gxt ft dt, where this gx is nothing but this is Green's function, and this will be your solution for this differential equation only when this gxt satisfies this condition. L of gxt means L is this complete differential operating on the g is giving you Dirac delta function that is infinite at x equal to t. So that's why we take the limit t plus and t minus, only that's why we take the limits. So if this satisfies this condition, then we see that in place of when you write the Ly, then in place of Lg, we will get this Dirac x minus t, and it will be defined for t equal to x only. So this will be fx. So that's why when this Ly becomes fx, and that is the case, Ly equal to fx, that's why this condition must be satisfied for this Green's function. So now we have finded the method to find this Green's function, and I told you that gxt is continuous and gxt d by dx of gxt is not continuous, because they both can't be continuous at the same time. And then I told you about the boundary conditions, that you need to solve them for the boundary condition a and b, and you need to find the solution for t less than, means a whatever x is less than t and x is greater than t. And then I told you how to find a, and the Green function was this. So we take an example also, and we solved, and the conclusion was, first we need to put this equal to 0, means Ly equal to 0, and we need to find the homogeneous solutions of y1 and y2. Then when we get the y1 y2, we need to find the a, only then we can write this Green's function. A can be found from this formula, where this pt is this function. So we solved an example based on this. Now let's solve some more examples today. So this is your question: d square y by dx square plus yx equal to fx, where y0 is given 0, and these are the boundary conditions at 0 and 1. So y dash 1 is 0. Now see, it can be written as dy dx fx dy by dx, and where this px is 1, means this can be written in this form, in this way. Here we write it as minus 1 dy by dx for the y double dash. If it is simply y double dash, there will be plus 1, so px will be 1. Now y double dash plus y equal to 0. Now solve. This will be this characteristic equation, lambda square plus 1 equal to 0. So lambda will plus minus iota. So solution of this equation will be cos and sine type. So here see, we don't need to find exact the solution, because c0 c1 must should be 0 for the trivial solution. So we just write the direct solution, means they should satisfy these condition only. So y1 at x equal to 0, it must be 0. So y1x will be sin x, because the solution must be y1 y2 must be sin or x sin or cos type. So y1x sin x will satisfy this condition. At x equal to 0, it will give you 0. And second, y dash 1 must be 0. So if you took y2x as cos x minus 1, then it will give you, means y2 dash will give you sin x minus 1, and sin x minus 1 at x equal to 1 will give you 0. That's why these will be your solutions. So by just saying this, you can assume that what your solution will be. So this must satisfy these conditions, and that's how you find this. Now y1 dash x will give you cos x sin x cos x, and this will give you minus sin x minus 1. Now you know how to find a. You need to substitute here. This is y2 dash t. So wherever y2 dash x is there, in place of x write t, it will be minus sin t minus 1, and then it will be y1x, that is sin t, minus cos t. Cos t is nothing but y1 dash x, in place of x write t. So this will be your, now it will be, take minus common, it will be sin x sin y plus cos x cos y, that is nothing but cos x minus y. So cos t minus t plus 1 will give you cos 1. So it will be minus of inverse of this 1 upon cos 1. So a will be minus 1 upon cos 1. Now you can write gxt as a y1x y2t x less than t, and a y2x y1t for x greater than t. So g will be this. Let's see one more question. Y double dash minus y equal to fx, and it is given that yx is finite for minus infinity and infinity, means in this range it will be finite. So at the boundary, means minus infinity, this should be finite. And from this, seeing this, we can say that px is 1, as in the last question we have seen. So characteristic equation will be lambda square minus 1 equal to 0, lambda will be plus minus 1. So now for this, solution will be of this kind: ex e minus x. So these conditions should be satisfied, means at the minus infinity it should be finite. So let y1 will be ex, because at minus infinity it will be 0. So that's the finite value. Now for infinity, let's assume y2x as e minus x. So at infinity it will be 0. So now these two functions are finite at minus infinity and infinity. So that's how we took these two functions. So y1 dash x will give you ax, and y2 dash x will give you minus e to the minus x. Now you have y1, y2 and y1 dash, y2 dash. You can write the a, and you can find the Green's function. Similarly, you have d square y by dx square minus y by 4 equal to fx. So boundary conditions are 0 and pi. So at 0 it is 0, at pi equal to 0. So it will, characteristic equation will be minus lambda square minus 1 upon 4 equal to 0. From here lambda will be plus minus iota by 2. Now the solution must be cos x by 2 and sin x by 2 kind. So these must satisfy this condition. So y1x assume sin x by 2, because at x equal to 0 it will give you 0. Now y2x must be cos x by 2. Then at x equal to pi this will give you 0. So these are the y1 and y2. y1 dash will give you cos x by 2 1 by 2, and y2 dash will give you minus sin x by 2 1 by 2. So this will be your solution. Now you have y1 y2 y1 dash y2 dash, so you can just find the a and you can find the g. Let's take one more question. D square y by dx square plus yx equal to fx, and these are the initial conditions are given. Y means boundary conditions are given. Y0 0, y pi by 2 is 0. So it will be, means again fx px must be 1. So lambda square plus 1 equal to 0, lambda will plus minus iota, so solution must be cos and sine type. So at 0 it must be 0, so y1x is sin x, and y2x at pi by 2 must be 0, so it will be cos x, because cos pi by 2 will give you 0. Now y1 dash can be find it, y2 will be find it, and just find the a value and write the g. And see, these cases we discussed are for the symmetric cases, means we have the both the boundary condition in the initial and the final. Sometimes question can be asked, means only the one boundary condition is given and you need to find the Green's function, and you need to find the complete solution also. That means only the two type of question can be asked from here, that find the Green's function or find the complete solution yx, and only this kind of question will be asked directly. You just put them like I told these questions, only this kind of question will be asked. So let's take the second problem, means now only one boundary condition is given at one end, and we call it as unsymmetrical, and it is initial value problem. So we call them initial value problem. So let's say it is given as d square y by dx square plus y equal to fx. And initial conditions are given only at 0, y0 equal to 0 and y dash 0 equal to 0. So two conditions are given, but only on the one boundary condition, means on the one boundary only. So again here px will be 1, and characteristic equation will be lambda square plus 1 equal to 0. So lambda will be plus minus iota. The solution must be of cos and sine kind. But see here the condition, according to the condition, it must be 0 at the simple function, and derivative must also give you 0 at the same value. So it is not possible for the cos and sine. And if you take cos, then it will give you minus sine for the derivative, and sine then it will give you cos for the derivative, and these conditions won't be satisfied for the 0. So the solution must be of sum of cos and sine. And if you take solution means sum, then this will also not satisfy this condition. Then we will assume that for t negative, means only the trivial solution is possible for this case, means y must be equal to 0. Simply this is the solution, y equal to 0. So, and this is the solution for 0 to t minus, means for x less than t, this will be your Green's function, that is gxt equal to 0. For this kind of cases, this will be your solution, gxt equal to 0. Must remember this case. And when there is no solution possible, then it is trivial solution possible, that is y equal to 0. So for x less than t, gxt must be 0. But the condition for greater than t is not given, so we need to find what is this case. Means let's assume a Green's function for greater than t, because the second boundary is not given, so we need to assume something. So for x greater than t, let's assume Green's function as c1t y1 plus c2t y2. So it is c1x y2x, c1t c2t. So we assume this Green's function, and this y1 and y2 should be of sine and cos kind. So let's assume that sin x and cos x. So c1t sin x plus c2t cos x. You must remember that what case you will take. So these are the general cases. So we know for the Green's function that gxt and g means if you take any t, means at gxt the function must be continuous at t. So it will be t plus and t minus, this must be same. So g t minus t and g t plus t must be equal, because x t plus and x at t minus, they must be equal to at t. So means that is the definition of continuity. So gt minus t equal to gt plus t. Now for the t minus, means x is less than t, that must Green's function is 0. We already find this thing here. And for the greater than t, we define Green's function as c1t sin x c2t cos x. and if we place the value t, substitute the limit, that is t, so it will be c1t sin t, c2t cos t. So let's assume this is equation 1. Now remember this case, means we defined for this when we see that this g must be continuous and then del g by del x must be discontinuous. So we find it this means for a t plus and t minus, this must be equal to 1 upon pt. So this is the case we did here. This is the case. So we just use this. So this must be equal to 1 upon pt. So pt is already we know 1. So del g by del x t plus. So this is your g. So for t plus this is your g. So it will give you cos x c1t cos x, then putting the value t, it will give you cos t, and then minus sin x, and at x equal to t it will be sin t. So minus c2t sin t minus 4g minus g is 0. So this will be 0. So this second one part will be 0. So this will be equal to 1 upon 1. Now from here this is equation 2. So it is c2t will be equal to minus c1t sin t divided by cos t. So substitute here for the c2t, and you can find the value of c1t and c2t using these two equations. And c1t will be cos t, c2t will be minus sin t. Now you can write the Green's function for the x greater than t, that is gxt as cos t sin x minus sin t cos x. So it is nothing but sin x minus y, means sin a minus b is nothing but sin a cos b minus cos a sin b. So it will be sin x minus t. Now you have gxt is 0 for x less than t and sin x minus t as for x greater than t. So you have find your Green's function for the unsymmetrical cases also. So this is the procedure how you find for the unsymmetrical cases and how you solve the initial value problem. Now see, in general we have this kind of solution, means for the it is given 0. So for less than 0 it is not defined. So yx is nothing but 0 to infinity gxt ft dt. Means see, we have a general solution for the Green's function, that is a to b. So a is given, that is 0, initial position is 0, but the b is not given. So we assume something t plus. So we assume that t plus as something x. So we just limit this at the t plus. So we take the outer limit as x always. When their outer limit is not given, you will take it as x. So 0 to x and gxt ft dt. So this will be your solution. So let's heavy side function is given in place of fx. So when we solve this equation, in place of fx it is given hx. So what is heavy side function? This is nothing but signum function, means for x greater than 0 it will be 1, for x less than 0 it will be minus 1. So this is your hx. So in place of fx this is given. So what is the solution if this is your hx? Then in place of ft you will write means for 0 to x, what will it is? It is 1 plus 1. So sin x minus t, gxt is sin x minus t for x greater than t. So it is 1 dt. Means remember here in this kind of cases where this only one boundary is given and initial is given, so you will just take it at 0 to x. So there is no that less than or greater, just write it as 0 to x and write this whatever gxt you are getting. So gxt ft dt. So for the heavy side function you have this. So it is 1 for greater than 0. So this will be 1 here and plus of ft. Now gxt it will be sin x minus t. So dt, this will give you minus, means minus cos x minus t divided by minus 1. So that will give you plus cos x minus t. Now 0 to x will give you, means for x t equal to x it will give you 0, cos 0 will be 1, and minus at t equal to 0 will give you cos x. So it will be 1 minus cos x. So this will be your solution yx. So must remember these cases. I discussed all the possible cases which is required for your exam. So no other question can be framed other than this we already discussed. So just try to do only these questions and that will be more than enough to clear all the questions in the paper regarding the Green's function. So that's it. Thank you everyone.